Welcome to this 7th workshop on acids and bases, and today we are going to look at pH calculations. We're first going to start with the problems that I gave for homework, and then I'm going to go through them. We're going to look at calculating the pH of a strong acid, and then the pH of a strong base. Then I'm going to introduce the concept of pOH, which is not explicitly part of the syllabus, but it is something that you can use. It's quite a nice method to use. I will teach you that. And then, depending upon how much time is left over, I might look at an old exam question that involves the concepts that we have taught you. So let's start off with the homework question. So the first one is, if 0.5 grams of hydrochloric acid is mixed with water so as to produce a 5 cubic decimeter solution, what would the concentration of the solution be? Now, that's a pretty straightforward stoichiometric calculation, but you got to get it right. Now, on your formula sheet, you have got the formulae for concentration. We are given the mass of the HCl. So we're going to use the mass of the HCl. This is number one. Right, so the mass of the HCl is going to be 5 grams. I just need to make 100% sure, 0.50 grams. And it produces a 5 cubic decimeter cubed solution. So we've got the volume of the solution is 5 cubic decimeters cubed. We are looking for the concentration of the solution. Now, on your formula sheet, you have that concentration is number of moles of solute over the volume of the solution. So they don't quite give it to you with the subscripts. They give you C equals N over V. But there's also another formula, and that formula is that N equals mass over molar mass. Now, we don't have the number of moles of HCl in 5 grams of HCl, but we can work it out if we get the molar mass of HCl. So if I take that, look at my periodic table, I know that hydrogen has got a molar mass of 1 gram per cubic decimeter cubed, and chlorine is 35,5. So this gives 36,5 grams per mole. Sorry, not per cubic decimeter, per mole. So this is the molar mass is 36.5 grams per mole. Now, we could then work out the number of moles and then the concentration, but, and I'm going to do this, I'm going to use the combined formula, which says that C equals M over big M times V, which you also find on your formula sheet. So what this formula does is it takes the number of moles of the solute and replaces it with the mass of the solute over the molar mass. So mass over molar mass and the volume of solution is V. So therefore the concentration is mass over molar mass times the volume of the solution. And now we have the mass of the solute, we have the volume of the solution, and we have the molar mass. So now we can work out the concentration. So we rewrite the formula, C equals M over big MV. We're wanting the concentration. So the mass is 5 grams. The molar mass is 36,5 grams per mole. And the volume of the solution is 5 cubic decimeters cubed. Now, we don't expect you in NSC in the substitution step to actually put the units in. But it's a good habit because it ensures that you're using the quantity in the correct units for that particular formula. So now we work that out. We say, okay, so we've got comma 5 divided by bracket 36,5 multiplied by 5, close bracket, so we keep the denominator together in the bracket. And that's going to give us that the concentration is 2,739,726 times 10 to the negative 3. I'm going to round off to 3 decimal places, 2,7. The 7 becomes a 10. Adding 1, the 9 becomes a 10. So this becomes 2,740 times 10 to the negative 3. And that is going to be mole per cubic decimeter cubed. So this is going to be mole per cubic decimeter cubed. And that is the concentration. So we do well to just check it, that we've done it correctly. If we go back to the question, it's always good to read. The mass is 0.5 grams of HCl dissolved into 5 cubic decimeters cubed of water to produce a 5 cubic decimeters cubed solution. We assume that the volume of the solvent and the volume of the solution are going to be the same. And then we will have to work out the molar mass, which we did. We said it was 36.5 for HCl. We substituted in 5 grams over 36.5 times 5 cubic decimeters cubed. So if we do that again, sometimes I don't trust my calculations. So if we do that, we divide by 36.5. It's good to just check it again before you move on to the next step, and that is correct. 2,740 times 10 to the negative 3 mole per cubic decimeter cubed. Now, if we look at the next part of the question, calculate the pH. Calculate the pH of the hydrochloric acid solution above, assuming complete ionization of the acid occurs. So in the NSC syllabus, we do not work with Ka and Kb values like we do at university, which are an indicator or a quantitative way of explaining where the position of the acid equilibrium is, and hence how strong the acid is when reacting with water. So we're going to assume full ionization, which means we can use the molar ratio of the balanced chemical equation. So let's take a look at number 2 now. So if we look at number 2, we say, all right, look at number 2, we say we want the pH. Now the pH is going to be the negative logarithm of the hydronium ion concentration. So we need that. We need the hydronium ion concentration. Now, in order to get that, we are going to need to work with the ionization equation for hydrochloric acid. And that's why I was insistent earlier in this workshop series that we focus on the ionization equation. So we take HCl, we've got HCl, and we add water, H2O. We're going to assume that the ionization step completely dominates. It's full ionization. And the HCl is a monoprotic acid. So we're going to have a single hydrogen ion or proton. Remember, hydrogen ion is just a proton being donated. So therefore, what is left behind is a chloride ion, and a hydronium ion is produced. Now, because of the fact that this is full ionization, we can now work with the molar ratio. So 1 mole of HCl will react with 1 mole of H2O to produce 1 mole of chloride ions and produce 1 mole of hydronium ions. So if you were to have worked with a weaker acid where there wasn't full ionization, then you couldn't work with the molar ratio directly, because some of what is produced would then be reacted in reverse, and so your molar ratio would be out. Your molar ratio still holds true for the change in the moles of each of these substances, as you will learn when we do chemical equilibrium and we do Rice tables. But for us with acids and bases, it would be problematic because we would not be able to use those coefficients for the molar ratio. That will make more sense when we do chemical equilibrium. So, but we're dealing with strong acids, so it's full ionization. So therefore we can say that the concentration of the hydronium ions in this solution is going to equal the concentration of the HCl. Because we're assuming that every 1 mole of HCl is going to fully ionize, producing 1 mole of H3O+. Every 1 mole of HCl will fully ionize to produce 1 mole of H3O+. So it's a 1:1. When you come to a diprotic acid, like we did with sulfuric acid, every one of these is going to produce 2 of those. So then it's going to be that your H3O+ would be double the amount of moles of the diprotic acid. So we can now say, well, okay, so this is 2,740. So we can say this is 2,740 times 10 to the -3. Be unit focused. So often learners lose marks because they'll do something like this and they'll go mole decimeter cubed. No, it's not mole decimeter cubed, it's mole per decimeter cubed. So either you have a line there or you put a minus sign, a negative sign in front of the 3. So now that we have that, we can now work out the pH. So the pH is going to be the negative logarithm of the hydronium ion concentration. And remember that there's an invisible base 10 there. So we write that down. You must write down the general formula first. Then we do the substitution. This is the negative log. And my suggestion is when you start to substitute in values, you change the square bracket to round brackets. 2,740 times 10 to the -3. It's not essential, but I like you to be aware of the fact that this square bracket represents the quantity of concentration in that solution. If you put square brackets there, you won't lose marks. I just like to differentiate between the two. It's a tiny little thing. It's not really important. Right, so now we're going to go the negative log of my answer to my previous calculation. And that's going to give me a pH of 2,56. 2,562. We want you to round off to 3 decimal places minimum, albeit that the NSC says two decimal places is enough. But we feel that if you do it to 3 decimal places as a standard, you can round off to more. It's fine. We are not very focused on the validity of the amount of significant figures you use in the NSC course, but we do become fussy about that when we do further studies in physics. All right, so the pH is 2,562, which is less than 7, which implies that this is acidic, which is what we would expect from this particular solution, being an HCl solution. Now, let's move to the next bit of homework, and that was to calculate the pH of a strong base. So KOH, with a concentration of 2,4 times 10 to the -4, calculate the pH of that solution. Right, so now we have that the concentration of the KOH is 2,4 times 10 to the -4. Now you're given the concentration of an alkali. So what we're going to do is we're going to say, okay, if we look at this here, we say, all right, we are looking for the pH. Negative log of the hydronium ion concentration. Okay, but this is unknown. So we need the concentration of the hydronium ion. Now, the problem is that we have been given the concentration of the KOH. solution, which is an alkaline solution. And we were told that that was 2,4 times 10 to the negative 4. There we go, 2,4 times 10 to the negative 4 mole per cubic decimeter cubed. So what we do now is we say, okay, so this is 2,4 times 10 to the negative 4 mole per cubic decimeter cubed. Right, there we go. And now what we need to do is we now need to say, well, okay, can we get the hydronium ion concentration directly from the concentration of the KOH? Well, answer is no. We need to first look at what is the dissociation equation of the KOH. So we're going to look at the dissociation equation. And the reason why it's dissociation is because this is already ionic. So no new ions need to be formed, as in the case with an acid, which is molecular, where it ionizes with water to form ions. Here, the ions already exist. So this is dissociation. So the dissociation equation of potassium hydroxide, we're assuming full dissociation when it's dissolved in water. In earlier workshop video recordings, we spoke in detail about why the H2O is there. It's a solvent and not a reactant. If it was a reactant, it would be on that side. The H2O, the actual molecular structure of the water, does not change. So therefore, this would produce K plus aqueous and OH minus aqueous. And the aqueous is basically the water, where the water molecules are now between the K plus and the OH minus ions. Now, looking here, we can use the molar ratio because of the fact that we're assuming full dissociation, right? So we can use it. If it was a weaker base, we couldn't do this. But in this syllabus, we work with pH of strong acids and strong bases. So it's a full ionization. So we can say that the concentration of the OH minus ion in solution is going to be the concentration of the KOH, which is 2,4 times 10 to the negative 4 mole per decimeter cubed. I'm purposefully writing it in a different form. Right, the decimeter cube now, I've taken downstairs, changed the sign, and now the sign of the 3 has become positive. Right, another way of writing this is as often as what chemists do and use in labs, is they have a big M in the unit there, and that stands for molarity, mole per cubic decimeter cubed. Now we go to the auto-ionization of water. Water ionizes, it's very small amounts of water molecules do this, but in essence what happens is, in a solution, water will have a certain small concentration of hydronium ions that are formed, and a small amount of hydroxide ions that are formed because of auto-ionization. So if I go back here, I'm going to go back here just to show you. Here's the auto-ionization of water, right? 2 water molecules in a very rare event will collide with a high enough energy and at the correct orientation that one of the hydrogen ions from one of the water molecules will stick, forming a hydronium ion and a hydroxide ion, which due to this water molecule losing its hydrogen ion to the other molecule. This results in hydronium ion and hydroxide ions in solution, but it's a very, 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 very small amount. Next, when we do chemical equilibrium, we will work with the equilibrium constant, which will then yield this at 25 degrees Celsius. So this is known as the dissociation constant of water or the ionization constant of water. It's a natural process. Now, we use that in order to switch between hydroxide ions and hydronium ions and vice versa. So this is going to equal 10 to the negative 14 at room temperature, which is 25 degrees Celsius. Right? So the hydronium ion concentration is what we're looking for. We know what the hydroxide ion concentration is, so we can say the hydronium ion concentration multiplied by the hydroxide ion concentration, 2,4 times 10 to the negative 4 mole per cubic decimeter cubed, equals 10 to the negative 14. Right, so now we're going to divide both sides by 2,4 times 10 to the negative 4. And so that's going to give us the hydronium ion concentration, which is going to be 10 to the negative 14 divided by 2,4 times 10 to the negative 4. And that is going to give us the following. Divided by 2,4 times 10 to the negative 4. And that's going to give us that the hydronium ion concentration is 4,167 times 10 to the negative 11 mole per cubic decimeter cubed. Now, I'm sure you will agree that that is a very, very, very small concentration of hydronium ions. It should make sense because this is in actual fact a basic solution. So, as opposed to when we were dealing with a solution with a pH of about 2.5, the hydronium ion concentration was of the order of 10 to the negative 3, whereas this is of the order of 10 to the negative 11. So it's 8 orders of magnitude smaller. So now we can substitute into the pH formula. pH equals negative log of the hydronium ion concentration. Always write the standard formula down from your formula sheet. That is good practice. Then write down your substitution step. Negative log of 4,167 times 10 to the negative 11. And so when we work that out, we get that the pH is 10,380, and we can see that this is it's a relatively high, not a very, very high pH, but a relatively high pH above 10, not quite close to 14, but it does point to the fact that this is more of a basic solution than it is an acidic solution. So these are basic. We've covered basic problems involving pH and concentration. Just remember that it can be made a little bit more difficult if we give you for instance, a base like CaOH2. Now, it says, let's look at number 2. 1.2 grams of KOH is dissolved in water and made up of a volume of 425 cubic centimeters. Calculate the pH of the solution. So now there's one extra step, is that we've now been given the mass of the solute and the volume. So we're going to calculate the concentration first. This is much like when we did what we did with the acid. And then we're going to have to use the ionization constant for water, that expression, to switch to hydronium ions to get the pH. But I want to teach you another method, which you can use, you're allowed to use, and I think it's pretty cool. So before we do number 2, I would like to talk to you about POH. Now, POH is taught at university, and if some of you have university students who are tutoring you and they do chemistry, they will more than likely teach you this method, because this method is very similar to the pH method, Instead of having pH as negative log of the hydronium ion, you've got POH is the negative log, base 10, remember the invisible base 10 of the hydroxide ion concentration. Now, what's nice about this is that it eliminates you having to work with the ionization of water, that expression. But we bypass that by doing the following. So we have been taught that if you take the hydronium ion concentration and you multiply it to the hydroxide ion concentration, that this is going to equal 10 to the negative 14. Now, I'm well aware of the fact that most of you have not done logs in this detail. Now, there are log laws that we use that really help us. So if we have, for instance, m times n, and we log both sides, we get log of m plus log of n. Right, the bases need to be the same. They don't have to be 10, they can be any bases as long as they're the same. Now, where this comes from is if you take two powers of the same base and you multiply them together, you add the exponents. 2 to the 3 times 2 to the 4 gives us 2 to the 7. So this is the multiplication addition log law. Now, if I log both sides there, if I log the hydronium ion concentration multiplied by the hydroxide ion concentration, can equal the log of 10 to the negative 14. Remember, one of the golden rule of equations is what you do to the one side, you must do to the other side. So I've logged both sides. Now I'm going to use the log of a product is the sum of the logs. So therefore, we've got the logarithm of the hydronium ion concentration. When I say logarithm, I mean the common logarithm. In other words, base 10. We're working with base 10, an invisible base 10. And this is going to be plus the logarithm of the hydroxide ion concentration. And now, I want to ask you a question. What exponent must you raise 10 to in order to get 10 to the negative 14? Well, negative 14. See, explicitly, this power is 10 to the negative 14. So when you ask what's the logarithm of 10 to the negative 14 to the base 10, what exponent must you raise 10 to in order to get 10 to the negative 14? It's negative 14. Now, if you know more about log laws, then you should know, and you don't have to prove this, that the logarithm of m to the n is the same as n times the logarithm of n. Now, what it means, this is what I call the upstairs to downstairs law. It comes from the fact that if you take a power of base b, if you take a power of base b, and you say m is a power of base b, what must you raise it to? So m is a power of base b, and you raise that to another power. Well, then we put the base down and multiply the exponents. So this is the one exponent, and this is the other exponent which we multiply together. So that would give us negative 14 log 10 base 10. But there's another law, the log of b to the base b is 1, we call the identity law, because what exponent must b be raised to in order to give us b? Well, namely 1. So this would then amount to negative 14 times log 10 to the base 10, which would be negative 14. Now, I want to say this explicitly. There's no need for you in this syllabus to be able to prove this, to work with this. It's nice for you to know where it comes from, but it's not imperative. It's not absolutely necessary that you do this. Now, what I'm going to do is I'm going to multiply both sides by negative 1. I'm going to take this side, multiply it by negative 1, and I want to take this side and multiply by -1. So I distribute the -1 through there, and I get negative log of the hydronium ion concentration minus the negative log of the hydroxide ion concentration equals 14. But wait a minute. Isn't this the pH? The negative log of the hydronium ion concentration is the pH. And I can put a little plus sign in there. Plus minus is minus. Plus the negative log of the hydroxide ion concentration is the pOH. And this gives us 14. So instead of using Kw equals the hydroxide ion concentration multiplied by the hydronium ion concentration equals 10 to the -14. In other words, instead of using this, we can then say, well, the pH plus the pOH is equal to 14. Now, this actually works out quicker when working with the pH of alkalis, as I will show you now. So if we use the other method. So if we now go back to the first question, calculate the pH of the solution of KOH with that concentration, then what I can do is immediately I can say, well, okay, we know that the hydroxide ion concentration is the same as the KOH concentration, which is 2 times 10 to the -4 mole per cubic decimeter cubed. I use big M as a unit for concentration. Now, the pOH is going to be the negative logarithm of the hydroxide ion concentration. It's the negative log of 2 times 10 to the -4. And when we work that out, we say, okay, so that is the negative log of 2 times 10 to the -4. And that's going to give us that the pOH is 3,699. Now, the pH plus the pOH equals 14. So therefore, the pH equals 14 minus the pOH. We take it across, which is 3.699. So therefore, the pH equals 10,301. And so if we now go and look, there is a rounding off error there, but basically we are getting the pH to be pretty much the same. There we go. So this is the difference, the slight differences in the second decimal place is rounding off, but the method is acceptable. So a lot of learners actually prefer this method when it comes to working out the pH of a basic or alkaline solution. They get the hydroxide ion concentration, work out the pOH, subtract it from 14 and get the pH. And so in the next problem, that's what I'm going to do. So let's now look at the next problem, which is 1,2 grams of KOH is dissolved in water and makes up a volume of 425 cubic centimeters. Calculate the pH of the solution. So we've got, let's go there, 425 cubic centimeters. So we're going to look at this. So we have that the volume of the solution is 425 cubic centimeters. The mass, I've got a very, very short-term memory, is 1,2 grams of KOH. Right, so that's 1,2 grams. The molar mass of KOH, well, K, reading off from my periodic table, K has a molar mass of 39, oxygen 16, hydrogen 1. 39, 16, and 1. So that makes 56. MKOH, this is number 2, is going to be 39 plus 1 is 40 plus 16 is 56. So this is 56 grams per mole. And now we want the concentration. So the concentration is going to be the mass over the molar mass times the volume of the solution. So that's going to give us the mass, we said was 1,2 grams. The molar mass is 56 grams per mole. And the volume of the solution is, we said was 425. Now I must be careful here. That's cubic centimeters, so we've got to divide by 1,000 to make it cubic decimeters. 0.425 cubic decimeters, we divide by 1,000. Remember, cubic centimeter is a milliliter, and a cubic decimeter is a liter. And there are 1,000 milliliters in a liter, right? So going from cubic centimeters to cubic decimeters, you basically divide by 1,000 because there's 1,000 cubic centimeters in a cubic decimeter. All right, I know that students sometimes struggle with conversion of units. 1 decimeter is 10 centimeters, right? And if you cube both sides, 1 cubed is 1, decimeter cubed is decimeter cubed, 10 cubed is 1,000, and centimeters cubed is centimeters cubed. There we go. Right, that was just a quick digression into conversion of units, where students often, or learners often make a mistake. So we can now say, well, this is 0.425 cubic decimeters. Okay, we've done that. And now we can work out the concentration. So the concentration is 1.2 divided by 56 times 0.425 downstairs. So I put them together in a bracket, and I get that the concentration is 0.0504. So the concentration is 0.5050 mole per cubic decimeter cubed. And whilst we're busy with this, you might be wondering, how does the mole go from there to upstairs? Well, can you see it's being divided? So different times, you flip it around, the mole goes upstairs, the grams cancel, it's mole per cubic decimeter cubed. All right, sometimes units can unsettle us. So now that we've got that, we have the concentration of the potassium hydroxide solution. So now we look at the dissociation equation. We've done this already. We've got that KOH dissociates into K plus and OH minus, right? And it's full, so it's 1 mole to 1 mole to 1 mole. So therefore we can say, and I normally use blue for hydroxide, the hydroxide ion concentration equals the KOH concentration, and that is going to be what we've worked out, 0.050. So this is 0.050, and that is mole per cubic decimeter cubed. Now, instead of now going and using KW, it's 10 to the negative 14, we are going to say, well, the pH plus the POH is going to equal 14. I made a mistake. I actually need to first work out the POH. So I'm going to say POH is the negative logarithm of the hydroxide ion concentration, which is going to be the negative log of 0.050, and that's going to give us negative log of 0.050, and that is going to be a POH of 1.301. Now the thing with POH, if your POH is low, it means your hydroxide ion concentration is high, but your pH is going to be high because we're going to subtract that now from 14. So pH equals 14 minus the pOH, taking that across. So the pH is going to be 14 minus 1,301. So the pH is going to be 12,699. And that is a high pH because this is a basic solution. We can see it should be a basic solution because the KOH concentration is very high, 0.05. So that is a high concentration. It doesn't seem like a high concentration, but it's a pretty high concentration. And so this is an acceptable way of working with the hydroxide ion concentration in order to get the pH. So always good to just check your numbers because it's sometimes easy to make a mistake. So I'm just going to quickly go negative log of 0.05. Sometimes we punch the wrong thing in. All right, I'm checking here. I didn't put 0.5, I put 0.05. It's correct, 1.301. And then subtract from 14. We subtract from 14, we get 12,699. And so with that, I'm going to end this workshop. What I'm going to look at in the next workshop is I'm going to do what we call a back titration together with a pH calculation. And I'm sure that will help you in preparation to practice for your exam, practice harder than you need to play. So thank you for that. And thank you for watching the video. And I hope this has helped you. And I will post this on YouTube. Thank you. Bye-bye.